Okay, so we'll start. The Ranguta method of order 2 is what we are going to start today, because last time you remember we talked about Taylor's method. So you write Taylor's expansion, right, at a certain point, right, by n plus 1, right, and then you approximate it with one derivative, it gives you Euler method, and you can go higher order derivatives as well. And then in that case, you can approximate the derivative, higher order derivative, by using the right-handed side function, right? Because y prime is equal to f, you all know. So y2 prime is f prime, but f prime is not necessarily a single variable function. So it's going to be a function of t and y, where y is a function of t. So you have to go chain rule and all sort of derivatives, and there are several differentiations you may need to do for higher order Taylor's method. That is what we saw last time. So then, in order to approximate the derivative, right, which appears in the Taylor's expansion by a series of approximations, that is basically by a series of functions, right? You know that in the Taylor's method, right? So that is, this is what we do, right? So in Taylor's, you know, yn plus 1 is equal to yn plus h time, right, f of tn comma yn. This is what we did in Taylor's, and we call it Euler method, right? So here the difference is you approximate the derivative by a different type of function, right, capital F, which you can think of as a slope, right? So obviously, you know, because of Taylor's expansion, you should have y prime here, and the meaning of y prime, you all know, it is basically a slope of the function, right? So you can think of this as the slope of the solution y, right, over the interval tn plus 1. So because when we talk about slope over the interval, then basically it's going to be an average of the slope, because at each point the slope might be different, right, depending on whether the function is increasing, decreasing or not. And then because of that, you know, you can think of capital F as an average slope of the solution, right? And then here, more importantly, we have the function capital F as a function of Tn, Yn, as well as the step size h, right? So for order 2 method, what we do is we do define or take the function in the following form, right? So that is b1 times f of t comma y. So that is what you usually have on Taylor's expansion, so Euler method, right, with b1 is equal to 1. So now this time you have a put extra coefficient b1 and then b2 with f over t plus alpha h, where alpha is again a variable, a constant which has to be determined, and y plus beta h f y, right? So this is basically, you can see that it is kind of an average slope, right? So this is how we define the Ranguta method of order 2, right? So now basically the goal is to first determine the constants, right? Alpha, beta, b1, b2 are the constant, and you may have to verify this, right? So how do you determine is this? Okay, so how we are going to determine the solutions, the constant alpha, beta, B1, B2 is such that the truncation error, right? So that is this minus this, right? So that is what we wrote here, right? By n plus 1 minus the right hand side, that is called the truncation error when you replace yn with capital Y, right? The real solution, capital Y, right? So assuming that this is the real solution, right, computed here, and then the original solution, right? So you can see that, right? So this is the real value, this is basically computed value, right? So the error is real value versus minus the computed value, but you do the computation assuming that the previous step, the real solution and the computed solution are same, right? It is not generally true in a numerical computation, you all know that, right? So the real value and the computed value are always going to be slightly different, but the meaning of truncation error is the difference between the real value at this point and the computed value at this point, right, at tn plus 1, assuming that the previous computed value, which is y at tn, is exactly same as the real solution. So assuming that here you have real solution, right, ytn, and then this whole bracket thing is a computed value at tn plus 1, and this is the real value at the end, so that is the truncation. So we determine the coefficients such that this truncation error is a function of h3 or is of order of h3, right? So the h to the power 3 should dominate the truncation error. So we have to compute this alpha, beta, b1, b2 such that h to the power 3 dominates the truncation error. So that is the idea behind the computation of this constants, right? So now we will see how we can try to do this. Right, so in order to do this, right, so in order to make sure that this one is order of h3, right? So basically you have to compute the constant such that this value is of h to the power 3. So obviously you know there is h hidden inside the function, right? So because h is hidden inside f, capital F, or basically h is hidden inside this function, right? So you may have to expand this function in a way to get h to the power 3. So when you want to get h to the power 1, 2, 3, and so on, so the best idea is to go for the Taylor's expansion. So that is what they are doing here, right? So they try to do the Taylor's expansion for the truncation error. So if you want to do the Taylor's expansion, then you have to do for capital F first, right? So let's do one by one, right? Okay, so we first see how we can do the Taylor's expansion for this second function, small f, right? So if we expand around y, then we try to stop after second order uh, approximation, right? So basically, if you expand according to the Taylor's expansion around y, then you know it is f of this, right? And then f prime of that times beta h fy, and then the rest is order of h squared, because then it is h squared over 2 factorial, then h cubed over 3 factorial, and so on, right? So eventually you get you can approximate after h squared. So the rest is order of h squared. So that is the first expansion. Now what we are going to do is we are going to do for other expansion. Okay, so now what we are going to do is to now what we do is we try to expand the same thing with respect to t, right? So if you do that, you get this f of right. So we expand around y with respect to second argument. Now we expand it with respect to t. So you get this f. Okay, so what we do is again we expand everything, right? All the terms here with respect to t. Right? So we try to expand the terms with respect to t. So if you expand the first term with respect to t, it is f of t, right? Plus f prime, that is this time f prime is with respect to t, right? So just for your information, I'll just write this here so you can see that. So you know that you can you see that now? It's right. So if you want to expand this, right? So if you want to expand this, you know that this is f of t comma y plus alpha h times f prime. So that is df over dt comma t comma y plus alpha h quantity squared over 2 factorial into d2f over dt squared t comma y, and you continue like this, right? So when you expand, you go like this, right? But obviously, you know, after this, all these things you can do it is order squared, right? So you already have an order squared, but when you expand this, you have another order squared, so you put it inside, right? So that's done. And then if you want to expand this part, right? If you want to expand this part, fy t, right, times this plus alpha h times f prime times this, but there is h squared, right? So you can see that now. Right? So f of t plus, sorry, fy of t plus alpha h comma y, and then you have a beta h f, right? So if you expand this, you know, fy times beta hf plus, you know, alpha h f whatever, right? So fi over dfi over dt, and then there is beta hf. So this term is already h squared. So any term higher than that is already h cubed, h4, h5, and so on. So you can combine all of them and put that as h squared. So that is why when you expand this and this, from this you have two terms, right? And from this you have only one term, right? All the others are got absorbed on h squared, order of h squared term, right? So that is why we leave it with only this number of terms, right? So that's the idea behind this expansion, right? So that's the rough work for you. But this is the expansion finally we have for the function f, small f of t plus alpha h, comma y times beta, and so on. Right? So that is what we have here. Right. Right. Okay. Now you know this. This is the original first order differential equation which we initial value problem which we work on. Right? So when we talk about Taylor's expansion, right? So when we talk about Taylor's expansion, we see this. So this basically implies, right? So I wrote it last time also, f sub t plus f sub y into f. Right? So you have this from the Taylor's method last time. Right? So when you approximate Taylor's method of higher order, this is something we did. Right? So you can take this. Thus, capital Y of t plus h is equal to, right, again Taylor's expansion. So y plus h times y prime plus h squared over 2 by 2 prime plus order of h cubed. Okay, so you know this y of t plus h, right? So this is something you know again by Taylor's expansion. Okay, so now you can make the substitution, right? For y prime and y2 prime, you can make this substitution. So I'm going to do that now. So this is basically y plus h times y prime is f, right? Plus h squared over 2 f sub t plus f sub y times f plus order of h cubed. Okay, so you have Taylor's expansion of yt plus h as well as y as well as the right hand side, right? So you have Taylor's expansion of everything, right? So now what you are going to do is you are going to substitute everything on the truncation error, right? So because eventually you have to substitute, you have to make sure that the truncation error should be of order h to the power 3, right? So you have to find constants such that the truncation error is order of h to the power 3, right? So now you can understand why I am doing all these things, right? Because if you look at the truncation error formula, right, there is already an h in front of capital F, right? So now let me write down the truncation error formula. So this is what we did, right? So this is t at or tn plus 1, right? Capital Y of tn plus 1 minus capital Y of tn plus h times what we write, f tn comma capital Y of tn with h. Okay, so this was your truncation error formula. So you can see that with capital F, I already have an h in front. So if I approximate capital F with order of h squared, when I multiply, I get order of h cubed, because your eventual goal is to get order of h cubed in this truncation error, right? So if I have h squared, that is enough for me here, right? Because when I multiply by extra h, I will get the h cubed. So that is why here we stop with order of h squared, right? So when you expand small f t plus alpha h and other that term, right? The reason why we stop with h squared, order of h squared, is because of this extra h here makes it order of h cubed at the end. But in this term, right, y of tn plus 1, you don't have any h term. So for this, you have to go up to order of h cubed, right? So that is why here we go to order of h cubed. So we go to second derivative, and then after that we approximate, just because we want to make sure we have order of h cubed everywhere, right? So now you can write this in terms of what we already have, right? So in a general concept, right? So let's see this. So this is actually that tn plus 1 is tn plus h. So instead of keeping those n's confusing, I just take t plus h, because if my time tn is t, then tn plus 1 is obviously t plus h. So you know that. So I'm skipping that part, right? So, and minus, this is capital Y of t plus h times capital F of t comma capital Y of t comma h, right? So now I have everything, right, such that I have the expansion, right? So now I need to substitute. So just start making substitutions. Okay, so let's start making substitutions here. Right, so that is basically equal to y of t plus h I have here. So that is capital y plus h times f, plus h squared over 2 times f sub t plus f sub y dot y plus order of h cubed. Okay, so that is y plus h, right? Y of t plus h. And then for this, you can write it down. First, I will write the function. So minus capital Y, right, plus h b1f, right, because you know your capital F is b1f plus b2 h of f of that function, right, so which I just erased. So you put the expansion there, right, so that is f plus alpha h f of t plus beta h f of y dot f, and then plus again an order of h cubed. Okay, so what you do is you just substitute everything, right? So because for this you have an expansion up to order of h cube, so you substitute. This is fine. H times f is b2 h times f. F is b2 times small f of that. For that you have an expansion, so you just substitute, right? And then what you do is you write it as a polynomial in h, right? So y cancelled out, capital Y minus capital Y cancelled out. So what you can do is you can start with the polynomial of h, right? So let me write down it. So you have h times 1 minus b1 minus b2f plus half, I'm writing here, half h squared into 1 minus 2 b2 alpha f sub t plus 1 minus 2 b2 beta f sub y dot f bracket closed plus order of h square, h cubed. Right, so you combine the like terms. So basically you combine the term with h, you combine the term with h squared, and then you combine the term with order of h cubed. So you have this. Okay? So you know that you have to find the constants such that the truncation error is of order h3. So you have to make sure that the term with h and term with h squared vanishes, right? So that means those coefficients should be 0, right? The terms with h and h squared should be 0, right? So that's how you figure out the constants. Okay, so 1 minus b1 minus b2 must be 0. For this whole thing should be 0, so this should be 0 and this should be 0. And so 1 minus 2 b2 alpha should be 0, and 1 minus 2 b2 beta should be 0. Right, so you have all three conditions. Okay, so here from this you try to see b2 can be anything, right? So b2 can be anything. Because you know you have three equations and four unknowns, right? So obviously you know you have to have infinitely many solutions, right? You study second year linear algebra, and you have three equations but four unknowns, so you have to write something free variable and all the others are dependent variables. So here I took b2 as a free variable because that is easy for me. And if I choose b2 as a free variable, then I can write everything in terms of b2. And so b1 will be equal to 1 plus 1 minus b2. And then my alpha and beta are equal. That are going to be 1 over 2b2. Okay, so that is it turned out to be very simple at the end, right? So it looks very complicated when we started, but when we end, it become very simple. So now you know that it all depend on what you choose for B2, right? As long as you choose something non-zero for B2, all the other coefficients fall into places, right? So we may have infinitely many choices for B2, but according to the book, there are only three favorite choices, right? So let me write it here. B2 are half, 3/4, and 1. Okay, so according to this book, right, the family of two-order Ranguta method, right, depends on the choice of B2, right? So B2 is the coefficient which associates this function, right? So it depends on that. But they say that you have three favorite choices around, and they are 1/2, 3/4, and 1. Right? So we don't know why they choose only those three as favorites, but maybe they are commonly used or maybe easy for calculation, that we will figure out if something exists on that. Right? So this is how you derive a second order Ranguta method. Right? So now you know how to derive a second order Ranguta method, and if you know the second order Ranguta method, and by choosing a suitable B2 among these three choices, you can always approximate a function by using the Ranguta method. And so in the next class, we will see how we can do that computation, right? And also we shall see a general framework to derive explicit Ramkuta methods, right? So those we will see in the next class on Monday, right? So I'll stop here and then continue on Monday.